All right, so this class actually has a lot of folks who have been thoughtful about this and have gotten this kind of worked out. If this is not you, then you need to catch up. So let's take a look at what's here. Most of you have a force downwards. Good job. So yes, there's definitely a force of gravity here. Either weight or mg, either's fine. Since mass wasn't necessarily given, weight would probably be best, but it doesn't really make much of a difference. We're going to be using mg quite a bit. At the same time, there is no normal force because there's no surface in contact with the sign. There are, however, two strings in contact with the sign, one of them applying a force to the right, one of them applying a force at an angle. I would encourage you to do the one at an angle first. The one to the right, you have no sense of scale for that one. But you know the one at an angle has to lift the box. It's the only one that applies a pulling force. So in deciding which one to do next, I would do the one where I can at least get an idea for scale. Remember, this part of this arrow has to be as long as this part for this arrow. So when you're dealing with scale, you have no scale for drawing to the right until you have something to balance it with. But we do know that this tension, which I will call T2, has to be enough in the upwards direction to balance the weight of the box. And yes, the size of the arrows matters. This one should be enough to the right to satisfy the fact that this force, is about that big. So I should be that big around. I'm gonna call this T1. Need a coordinate system. This object's not accelerating, so I'm gonna choose a coordinate system that's aligned with my two forces. The third force is off axis, but I can at least line it up this way. And positive y, positive x, negative y, negative x. You guys who refuse to use your ruler and continue trying to make these super small, that's going to work against you tomorrow. If it's not big enough that I feel like you've really taken enough time to make the scale appropriate, I will just have the student grading it, give you 0 points. Use some paper. It's okay. Paper's inexpensive. Now you have to identify reference, and this is theta here. I know this because of putting a parallel line here. Tells me that these two angles have to be equal due to alternate interior angles. I'm sure you remember all of your geometry. So alternate interior angles, corresponding angles, alternate exterior angles. You should know which ones are equal to each other because we use that kind of stuff all the time. Let's see. I have decided on my coordinate system. I need to break my off-axis vector into components. As I said kind of on Friday, I am not doing your trig for you anymore. Although this is T2, this is going to be T cosine theta. I'm sorry, T2 cosine theta. This one's going to be T2 sine theta. You may need to write out opposite and adjacent and hypotenuse and do all that stuff. That's fine. Get faster at it. You don't want to have to spend a lot of time doing triangle work. Understand that it's going to be T2 and it's going to be scaled by the angle. So the adjacent one gets cosine and the opposite one gets sine. Once that's established, net force in the x direction equals 0. Net force in the y direction equals 0. There are two forces in the x direction, T1 minus T2 cosine theta. That equals 0. Add up all the forces, taking into account their direction, and set them equal to 0. And in the y direction, I'm going to have T2 sine theta minus weight equals 0. That's what my expectations are. You are producing two relationships that could be used to solve for the forces of tension in this case. Now, getting the diagram, getting the picture, that's just the start. It's what you do with these that matter. There are things you could do here. The first thing I'd like to point out is this produces relationships that tell you how T1 and T2 are related, but it also tells you how they're related to the weight of the thing you're trying to hold. So if you're trying to figure out how much tension is in the cable, you can do that. You've got the fact that T2 sine theta equals the weight, so you know how big T2 is going to have to be. And right now, this tells you right away that T2's got to hold more than the weight of the cable, right? Sine of theta is going to be less than 1. So doing it this way automatically requires cables that are beefier than what you're hanging. It's important to know that people buy stuff and don't necessarily understand this. They need to. But I'd also want you to consider that T2 sine theta equals weight, while T2 cosine theta equals T1. You could get an idea for what T1 has to equal as well by just looking at these two. If you're paying very close attention, I would probably divide both of these equations out. The left side cancels out T2 and gives me tangent of theta equals weight divided by T1, which tells me that T1 has got to equal the weight divided by tangent of theta. That angle makes a big difference as to how much force these cables are going to have to take. Questions yet? Do you see why, if you can't get the picture right, how you're never going to get this kind of stuff? All right. Let's do the next one. All right. Example number 5. Take it easy on you with this one. Go back to something that maybe is a little bit more simplistic, something you've done before. I've got a wagon. The wagon's being pulled by a child. The child attaches a string to the wagon and pulls at an angle of theta relative to the horizontal. The wagon is moving to the right at a constant velocity. Identify all the forces acting on the wagon. Do this. So, first law problem, they all are. Reduce my object to a point. Think there's a conservative force. There appears to be a rope or string attached to the object. So I'm going to draw a force in the direction of that rope or string. Don't think the string is the length of the vector. Choose appropriate lengths, but I'm not sure the string is the length of the vector. It's not lifting the wagon off of the table or off of the floor, but it is pulling to the right and upwards. I'm going to list this as a tension. It's in contact with the floor. So there's got to be a normal force. Somebody asked, can you have normal in tension? Sure, why? Why not? If it's in contact with the surface and has a rope pulling on it, then it'll have a normal force from the floor, and the rope causes a tension force. This looks unbalanced to me, suggesting that there should be something maybe this way. What's a likely candidate for this way? Yeah, that's a likely candidate. And there's rules about friction. Friction is parallel to a surface, while normal is perpendicular to a surface. You don't get to make choices here about some of these things. If it's in contact with the surface, the direction of the surface dictates the direction of the force. That's perpendicular to the surface. That has to be the direction of the normal force. Friction has to be parallel to the surface, so friction is going to be perpendicular to normal. And there is no friction without normal. Now, the fact that this is rolling, that adds a complication that we'll come to later for dealing with rolling friction. But it's still going to behave like friction for the time being. I would probably choose a coordinate system that's aligned with the three forces that are all perpendicular to each other. That seems like the right choice to me. So positive x, positive y, negative x, negative y. And for those of you who aren't doing these things, it doesn't take me very long to do it, so I'm sure it won't take you very long to do these things either. I see that I have one of my forces off axis. That's got to be theta. So I think I'm going to write this as tension cosine theta, and this one as tension sine theta. Net force in the x direction equals 0. Looks like T cosine theta minus friction equals 0. Net force in the y direction equals 0, so T sine theta plus normal minus weight equals 0. If I wanted to pull the wagon off of the floor, I think the answer to that question is here. Do you see what you would have to do? Are you sure? Because I know the condition that has to exist in order to find that out. Do you see it here? When it's no longer touching the floor, then you've pulled it off the floor. So I would like to find a T that would reduce N to 0. That's how you would find out how much force is necessary to pull it off the floor. You see, normal force is a responding force. It responds to other things that are happening in your system. If I push down on the wagon, the normal force will increase. If I pull up on the wagon, the normal force decreases. The normal force only exists because the wagon's in contact with the ground, but how much force you get for the normal force can change depending on the conditions of the problem. If they were pulling more to the side and not upwards, that would reduce how much they're pulling upwards on the wagon, and the floor would have to increase the normal force to support the wagon more. That's what I mean by saying the normal force is a responding force. It responds to changing conditions of your problem. Be prepared to manipulate the normal force in dealing with these kinds of questions, to ask yourself about conditions that could exist. And guys, I'm giving you things to be thinking about. I would encourage you to perhaps write those down. I call the normal force a responding force. It responds to the conditions of the problem. So when you hear that phrase in the future, understand it means it could change under the conditions of the problem. Or don't write it down. You're the one who has to pass the test, not me. Go to the next example. I'm going to actively try and trick you here. And I will be successful for some of you, but maybe not for many. I've got an elevator with a person inside. The elevator is moving downwards at a constant velocity. The person in the elevator has a mass of 60 kilograms. I would like you to draw a free body diagram for the person, please. Part of your question. When you're asked about what's happening to the elevator, that's one question. You're asked about the person, that's a separate question. The person is experiencing two forces. They're experiencing weight downwards, and they're experiencing a normal force upwards, and those should be balanced. They are not experiencing tension. The cables connected to the elevator box, they are not connected to the cable. They experience a normal force because they're in contact with the surface, the floor. Their weight is 60 times 10, right? 600 kilograms meters per second squared. The unit of force is the kilogram meter per second squared. This is also known as a Newton. So be aware, a Newton is a complex unit. It is the unit for force. So when you're finding a force, you'll be finding it in newtons. There are 10 newtons in every 2.2 pounds. Pound is the English unit for force. Kilogram is mass, pound is not mass, pound is force. So the actual English unit for mass is the stone or the slug, but we tend to not know that or use it. So pounds and newtons are both forces. If you wanted to find a conversion for your current weight in newtons, there it is. Take a minute now and find a free body diagram for the elevator. The box is being pushed up the ramp at a constant velocity. I am interested in what's happening to the box. I don't care about the kid. Everybody understand? Okay. There's some things here that you'll have to make decisions on, sure. But some of them are very prescribed. Your job is just to follow the prescription. If I reduce the box down to a point, and I begin by drawing, say, the weights, something I think we can count on. When I start looking at contact forces, well, it's touching the surface of the incline. I don't have a choice here. The incline is this way. So I have to draw this force perpendicular to the incline. Now, once I've drawn this is the normal force from the ramp. The person's pushing on the box. You could probably classify that as another normal force, which would have to be perpendicular to this surface or up the ramp. Now, whether you want to just list this as an applied force from the person or a normal force from the person doesn't matter. We're trying to find ways of organizing the forces that are acting on the box, and to the best of your ability. Now, I don't know that there has to be a frictional force or not here. Right now, it's unbalanced, and I would say for it to be constant velocity, there would have to be something pulling to the left. But there's already a portion of the weight pulling down the ramp. Whether or not there's friction here may depend on the nature of the question. They could say things like it's a smooth ramp or it's a rough ramp. Words like that matter. Smooth suggests little to no friction. Rough suggests there's friction. You'll need to pay attention to those subtleties. But based on the way I've drawn this, I think it would not be unreasonable to expect that there is a frictional force acting this way. Friction has to be parallel to the surface. Has to be parallel to the surface. So if you're going to draw it, that'd be the way to draw it. Now, you have choices on what you do next. I think it's not unreasonable to do a coordinate system aligned with these forces as they represent 3 of the 4 forces that are all perpendicular to each other, and the weight is the only one that isn't. Of course, you're going to have to do some soul searching to figure out where to put this. I'd start working out where that goes. I start working out where it goes, and be thoughtful about it. As this goes to 0, which one of these would go to 0? Start be thinking about how to figure out where the angle of the ramp goes. I don't think this is a lot to do, but I'm going to say it anyways. This is weight in the Y direction. This is weight in the X direction. Understanding where that angle goes makes a big difference because it's going to determine which one of these is sine and which one of these is cosine. And you have to get this right. So weight in the Y direction is weight cosine theta, and weight in the X direction is weight sine theta. Since this is a first law problem, net force in the X direction equals 0. Looks like I'm going to have the normal force in the person minus the weight sine theta minus friction equals 0. Any questions about that? All right. Net force in the Y direction equals 0. That seems to be the normal force in the ramp minus W cosine theta equals 0. There's a set of rules. I'm applying the rules the same way every time. Are you? Look, before you walk out the door, step 1 was to determine which one of these functions it is, first or second law. Step 2, free body diagram. Step 3, drawing a coordinate system. Step 4, breaking up your off-axis force into components. Step 5, applying Newton's laws and generating a relationship. This is what you have to do. These are all the steps.